Okay, good afternoon, everyone. Thanks for joining us today's GW4 Water Security Alliance webinar or seminar. We are in hybrid mode, and I'm very glad to see so many audience in this room and also online. And so today we have Esteban Sanuto from the University of Corona in Spain. So he's visiting us today in last couple of months. So it's the final week he's staying with us, but he gave us some of the audience in this room last month about what the facility they're doing in Spain. So today he's going to give us more detail about the experiment he's been doing and all his research on the urban flood modeling part. So let's welcome Esteban.
Thank you, Albert. Well, as Albert introduced me, I'm Esteban Sanudo. I'm a postgraduate researcher, a PhD student of the University of Coruña. My background is the development and validation and calibration of urban drainage models, and also the application of these models to large-scale cities. And also, as a part of my PhD, I also work in experimental hydraulics. That's the thing that I'm gonna introduce today in this presentation, that is called experimenting a large scale urban physical model for the validation of 2D, 1D numerical models. So, as online, I want to talk about urban drainage systems, then introduce a little the urban drainage experimental facilities that we have in the University of Coruña. Then specifically, I'm going to talk about my facility where I carry out the main test of my PhD. I want to talk about the experimental tests, how I did these tests, and then the results and the conclusions. And finally, we introduce the use of this data that I obtained to validate the urban drainage model that is covered Iber-SWMM, that is a main part of my PhD. And we are introduced very briefly how can you use Iber-SWMM in large scale models. Let me introduce first the problematic, why we need urban drainage models. Now cities are more impervious due to urbanization, and if we link that the climate change, we have an increase, the risk of flooding is increasing, and also its consequences, not only flooding, also with the pollution, in the pollution, also pollution to the environment. So it's very important that cities have urban drainage systems properly designed, and for do that, engineers, designers, and other people need urban drainage models that works properly and that that's going to be validated and calibrated for these specific cases. One of the equations and the use of the model, validate. We can use that to validate these models because we have less uncertainties in this kind of data sets. Well, only one slide or what is or you maybe know it, but it's important to have a conceptual scheme of how works urban drainage model, urban drainage system, sorry, in a city. The main objective of the urban drainage system is to evacuate, to drain, direct and quickly the water of episodes to the wastewater treatment or to the environment, like all of the main elements of the system are roofs, the inlet, the surface, the manholes, the pipes, and the outflows. And it works in a holistic way. I mean, it's an integrated system. The roof are important because that's the water that holds in there. The surface also convey the flow through the inlets, and the pipes, manholes are the properly sewer system that cannot be properly designed. And on the other hand, we have how this works. I mean, in normal conditions, the water enters through the inlet to the sewer system. Also, the water of the roof is conveyed to the sewer system, but in surcharge condition, we have the opposite direction. The capacity of the urban drainage system is exceeded. The system can overflow and provoke flooding at the surface. So, to properly design this system and to validate our models, we need a data set of we need data to validate this model. So we must to make experimental tests in urban drainage facilities. For example, this facilities are the facility that we have in the University of A Coruña, that we have a street that is a 36-meter square street with a rainfall simulator and urban drainage system. Then we can analyze flooding and pollutant processes. Also the block that is similar to the street, but we are buildings to the facility. And finally, a channel located in a wastewater plant that we can install there pipes to analyze processes of transport in the real wastewater. In my case, I carry out my PhD in the block facility. I'm gonna introduce now all these facilities are available within a project that is called the Labs, that is a project that offers free access to urban drainage facilities around Europe. The first call is now finished, but we have a second call at the end of October 2023. This project is integrated by 9 partners, 4 universities, Coruña, Sheffield, Lyon, and Aalborg, and 10 institutes like Deltare, Seabaja, KT, and 2 organizations, Novia, and Gray. These are all the facilities that you can engage in the project with different purposes. If you are interested in this project or can use these facilities, we provide free access. So you have the link of this project there. So you have, if you want more information, you can. In the block facility, that is the facility where I carry out all my experiments. Is part of these experiments are funded by the Spanish Ministry of Science and Innovation within a project called Saturno, that is early warning against flooding in urban areas. Now I'm gonna get deeper in this facility. Facility has 100 meters square area. It's a very big facility, and also we have one of the biggest rainfall simulators equipped in the facility. You can see there the rainfall simulator. The facility is linked also to a sewer system, a real sewer system with pipes, manholes, and a outflow. And the rainfall simulator can generate intensities of 30, 50, and 80 millimeters per hour with a very accurate results. This is a scheme of the facility. We have 4 roofs that are, as I said before, roofs are very important in urban drainage because the surface of the city has a lot of footprints of buildings, and it's important to consider the effect of the roofs in the network. So we have 4 roofs, 4 manholes, 2 main pipelines, 4 inlets, and then last inlet at the end of the boundary of the.
Could you use this one to see the better microphone?
Okay, it's better now.
Would this audience let us know the audio better now? Please just raise your hand, or
someone can.
Yeah, better.
Thank you, Rob. So, well, that's the scheme of the facility. I continue. And we have also, that is very important, we can introduce runoff over the upstream ridge, and we can include also pipe inflows in the top of the pipes, in the top of the pipe, to simulate the effect that could have other neighborhood upstream in the facility. Now we are going to see. This is a promotional video of the facility. All the things that I explained are collected in this video. This is the facility. This is the rainfall simulator working. As you can see, it's real, it's completely real rain. That's the roof with the gutters. And this is, as I say, the rainfall, the runoff generator that we can put runoff in the surface to simulate the effect of upstream street or upstream neighborhoods. But now this is the reconstruction of the facility that I'm going to talk about this later. We have a very good 3D model of the facility. It's a topography. And also is part of the project to measure velocities on surface and how the flow is going through the inlets. This is the sewer system. That's where we can put the input flows. And the output. That's the output with the triangular way. Well, I focus it on this slide focus on the roof because we can put and we can play with the slope of the roofs to test if roofs have effects or not in the downstream outlet. The roofs are real roofs with a gutter, with a 1% flow gutter. And next tests are going to introduce green roofs to the facility test the effect that we have in the outlet of the facility. So now I'm going to talk about how we carry out the experiments and how we acquire the data. I short this in 3 word packets. That was the characterization of the rain, because it's important to know how many water is falling. The second block is catch all the topography of the facility, and finally, obviously, make the experimental test. To characterize the rain, we put 325 vessels over all the surface and over all the roofs. And during 10 and 20 minutes, we catch all the water that is dropping in each vessel. Then with the volume and the mass, we have the intensity. And we can do, this is the grid of vessels, and with this, we can do the raster of precipitation or raster of rainfall intensity. That we plan it 30, 50, and 80 millimeters per hour, and we obtain it 30.3, 54.2, and 85 millimeters per hour, so we have a very good system, and we can and the good thing is that we can replicate it, the test, because the rainfall simulator are very accurate in terms of the intensity. I mean, we have a variability of 2 millimeters per hour when we repeat the test. Well, to simplify, if I put 30, 50, and 80 because it's not common put all the decimals to, it's only to conceptual. The reconstruction of the surfaces are doing with this sensor that is like a tennis ball, very small, and we run all the surfaces, all the roofs, and reconstruct all the surface. We are with a computer, with a good performance computer, and is classical LiDAR, but we can have a very, very accurate representation of the surface in a point cloud. After post-process this point cloud, we obtain the digital terrain model or digital elevation model of the facility with a 5 millimeters cell resolution. The map that we are used later to validate the equation and the model. Finally, we measure all the other things necessary to have a complete data set, that are the slopes of the pipes, the diameters, the position, and all the things that is necessary, all the geometries that will be necessary to build a numerical model. Well, regarding the experimental pressure, we test 6 different piezographs, 3 constants, 2 intermittents, and 1 variable. And we measure discharge on roofs, discharge on inlets, and finally discharge on the outlet. In addition, we also put ultrasonic sensors on the surface to measure the depths of water in different points of the street. To measure the discharge on the roofs, we put a tank downstream the gutter, and indirectly, using levels, we can know the time step between each measure. We can take the discharge. Yes, take off this. Okay, that's regarding roofs. Regarding inlets and regarding the outflow, it's similar. We put a triangular wire inside the galley, the outflow, and also with a curve with the discharge and with the depth, we can know how many discharges passing through how many discharges catching the inlets and the wire. That's some result. I'm gonna talk about results only to see how will be the form of the result that we are going to publish in a data set. We have some proofs, the inlets and the outlet for each intensity, and then we have a specific analysis of results in proofs that are now published in an article that I see later. So, well, the conclusions of the experiments are that we have experimental tests in a large-scale urban drainage facility. We consider all the sewer and surface processes, including the bidirectional exchange, and we provide a high-resolution data set with accurate data of rainfall intensity, topography, and all of this. This data set will be available as possible. I don't know exactly when I finish it to package that. Just today, this article was published. Is the first part of the research, and that we compare the numerical and experimental. We validate numerical models with this experimental data, and we also study how how resolution is needed to model a roof. If we can model all the tiles, or if we can model a slope plane, or we can do a lumped approach, and what's happening with that. And that's finally, all these experiments, we are going to replicate it in a 2D, 1D urban drainage model. That's the first part of my PhD, that I couple a 2D overland flow model that's called Iber, and SWMM, the typical water model. This is a high resolution model. We consider all the processes, and we also implement the two-directional exchange between the surface and the thing that I put in the second slide. That is very important to consider. If the sewer is surcharged, what's happening with this water that comes again to the surface? All the people know SWMM, but they present that it's a two-dimensional hydraulic model. Is free. You can download free from Iberaula.com, and you can Iber has a lot of capabilities as river inundation, modeling hydraulic structures, land breaking, now urban drainage, and other sediment transport, water, etc. And now in the official version is not coupled with SWMM. It's gonna be maybe at the end of this year. We have a plugin we can use also the linking with SWMM. That's for the official version, but if someone is interested in use it, we distribute to academic purpose the software, the code. Well, we see first the real facility, now the numerical facility stat in the top Iber, and below SWMM is the main, that's the main pipe of the facility in SWMM, coupled, and both models are completely linked coupled. So that's results. The maps, the surface, and then all the data that is obtaining for the different points that we measure experimentally. The maths, the fitting is not, I'm not present now because I must work on it, but at the first, the preliminary results. And it's good, but it's academic purpose, and we must transfer this to the industry, to engineers, to private sector to use this model. So now we are starting here to apply all these experiments, all these models, and all these validations to large scale urban cities like this one that we have. We consider we consider surface flooding, and also in this settlement is considered the urban drainage. And that's what we have. When it starts raining, all the cities flooding, and then with the urban drainage system is evacuating all the water when it stops rain. And that's all from my side. I will acknowledge to Luis, Jerónimo, Jose, Joaquín, Juan, Manuel, Gonzalo, and Gabriela, and all the CITEC staff, because these experiments are difficult. It implies a lot of work and a lot of time. So without their help, maybe this presentation is not take a good final.